Hi, my name's Tom Green. I work in the Knappenberger Research Group in the Department of Chemistry and Biochemistry at Florida State University. And today I want to talk about quantum dots fluorescence and how you can influence it with the magnetic field. So just to give some background, quantum dots are a widely studied species, and it's largely because you can tune the band gap by controlling the size. And the band gap determines the emission color of fluorescence, as you can see in this picture. And this tunability makes quantum dots a technologically really interesting material, because you could imagine a device where you have quantum dots arranged in order of decreasing band gap so that you could get a vectorial energy flow across the device. This is an interesting topic in light harvesting and solar energy. It turns out that the efficiency of this energy transfer is proportional to the quantum yield. And so it's important to be able to understand the fluorescent properties of the quantum dots. So here's a diagram of the fluorescent process in a quantum dot. And the first step is excitation above the band gap. So you take an electron from the ground state to an excited state, and that's followed by relaxation to the lowest excited level. In a quantum dot, the lowest excited level has some fine structure, and so there's a couple different pathways that it can go through. The first one is that you can get relaxation through phonon coupling, and this is less desirable because there's a lower probability that this will happen. What we'd like to happen is fluorescence. And so if we can find a way to get electrons out of the relaxation through phonon coupling and promote them into the fluorescent pathway, that would be ideal. And so here is a spectrum of the fluorescence, and the goal is to increase the intensity. One way to do that is to introduce a magnetic field. And so when you introduce a magnetic field, degenerate levels split. It's called Zeeman splitting. And in this system, that means that the energy difference between the bright state and the dark state decreases. So the states mix, and it's easier for electrons to be promoted into the bright state, and fluorescence increases. And so here's the spectrum. Again, you can see you do in fact get the increase in intensity. And if you plot this versus the applied field, you can see that up to 10 Tesla, you get about a 25% increase in fluorescence. So that's okay, but we'd like to do better. And so the next thing to think about is how the quantum dots are oriented in the magnetic field, because it makes a difference. And here's a diagram of the sample where you have a glass slide with quantum dots deposited on the surface. And because they're roughly spherical, they are randomly oriented on the slide. To get the best enhancement using the magnetic field, we need a specific orientation so that the magnetic field is perpendicular to the c-axis of the crystal lattice, which is represented by the black arrow. And so you can see that since they're randomly oriented, we don't get the maximum possible enhancement. So we need to find a way to orient them. And one way to do that is to go from zero-dimensional spheres to one-dimensional nanorods. So now we can grow nanorods so that the long axis of the rod is also the c-axis that is important for the orientation. And that will always be horizontal to the slide. So now when we introduce the magnetic field, it's always perpendicular. And when you make the same plot, you can see where before we had a 25% increase in photoluminescence, we now get a 300% increase, which is a lot better. So just to conclude, quantum dots are an attractive building block for designing new materials in a wide array of fields. The fluorescence can be enhanced by the presence of a magnetic field, and controlling the shape and orientation is vital for maximum enhancement. Thanks for watching my presentation, and thanks to Dr. Knappenberger, my research group, Harry Croto, and the GEOSET crew.